Good morning, everybody. Thank you for those that can make it in person, and thank you everyone that is online today. So welcome to the Planetary Sample Science Seminar Series, again hosted by the CASA Moon team, by Survey Central, by the UNM Grand Challenge, Institute of Meteoritics, LPI Lunar Planetary Institute, and RASL. And so today we have Alex King is going to be giving a talk today. So Alex got his bachelor's from Stony Brook, where he was a member of the RISE team back in 2020, and currently is a fifth-year PhD student and a NASA Finest Fellow in the Department of Earth, Atmospheric, and Planetary Sciences at Purdue. And so, Alex, I know you have a lot with the regoliths, so I will let you take it away from here.
All right, thank you very much. Can you hear me all right?
Yep, we hear you perfectly.
All right, great. So then I'll just get into it. So thank you all for attending. Today I'll be talking about the nanoscale storage of solar wind volatiles and their retention on the lunar surface. And I'd like to just start off by saying I'm happy to be giving this talk as part of Survey. Survey has a close spot in my heart because my first conference in undergrad was the NASA Exploration Science Forum. So yeah, I'm a fan of Survey and happy to be here. And so talking about Survey, I first want to touch on some of the relevance to Survey science and exploration priorities that my work touches on, such as sample science and geochemistry, regolith of target bodies, dust and plasma interactions, radiation and space weathering, as well as volatiles and what we could do with those volatiles through in situ resource utilization and prospecting. And I'd first like to start off with giving a background on some of our perspectives of the study of solar wind volatiles at the moon. One of the ways that we know about solar wind volatiles at the moon is through exospheric observations of these solar wind volatiles from a number of missions through the last several decades, such as the LACE mission as part of Apollo 17, the LADEE mission, and the Chandrayaan-1 Explorer as well. And just an example of some of the information that we can get about solar wind volatiles in the exosphere. On the right, I have an example of a distribution of solar wind neon in the exosphere as seen by CHASE. Another way is through the analyses of samples, specifically using extracted gas analyses of lunar samples. One thing to note is the most definitive way that we can identify volatiles as being solar wind derived is based on their isotopic signatures that we could get from these mass spectrometric analyses, either in the lab or in the case of exospheric observations, in some cases by orbit. And so on the right is an example of some data from an Apollo core sample of different noble gases, solar wind derived noble gases in the regolith, as compiled by Curran et al. 2020. And we've also seen evidence of solar wind, hydrogen, and water in lunar samples as well, based on these isotopic analyses. So I mentioned isotopic analyses are the best way for us to be sure of that solar wind origin, but there are other ways that we can intuit this relationship. We can also have an understanding based on remote sensing observations of the lunar surface. In this case, through the observation of OH or H2O via the 3-micron hydration feature on the lunar surface. Here's an example of that from the Deep Impact mission. And while, again, we can't directly tie this to the solar wind based on its relationship with other observed parameters like time of day and solar wind flux and these things, we can point towards this being of solar wind origin. And this is also supported by laboratory experiments that simulate solar wind irradiation in analog materials and can replicate this 3-micron absorption feature as well. So moving on, so that's a bit of our understanding of solar wind volatiles at the moon. And so I'd like to talk about the process that puts them there in the first place, solar wind irradiation. So just a brief overview of some of the general things we know about solar wind at the moon. The solar wind is primarily composed of hydrogen ions, around 96%, around 4% helium ions, and less than 1% of our heavier ions. The nominal solar wind has an energy of around 1 kiloelectron volt per atomic mass unit, And for our primary ions in the solar wind, they have a flux of, for hydrogen, about 1 to times 10 to the 8th ion per centimeter squared per second, and for helium, around 5 times 10 to the 6th ions per centimeter squared per second. And I'm next going to talk about some of the effects that we see due to solar wind irradiation at the moon. First, I will be talking the small scale, which is what I study specifically at the grain scale. So we have, here is a very basic schematic of a single lunar grain exposed at the space environment at the lunar surface. And so we have hydrogen and helium implant into the surface. It can implant around 100 nanometers into the uppermost region of the grain. And while it does that, it can sputter away atoms that are present in that host material that could be either redeposited or lost to space and enter the exosphere. At the same time that the sputtering happens, these energetic ions are also continuously disrupting that original crystalline structure, denoted by this around 100 nanometer thick solar wind damaged rim overlying our original crystalline interior. And yeah, a combination of that sputtering and the high energy ions being implanted can disrupt bonds and generally create disorder in our lattice structure where we may have originally had order. So you can have vacancies, you can have just damage to that crystalline material, and in some cases full amorphization depending on the mineral phase. And as this progresses, we can have more complex defects and effects occur. For example, you can have those vacancies start to diffuse together over time and form larger scale defects such as vesicles. You can even have those smaller vesicles in turn diffuse together to form even larger ones that can extend to be up to tens to maybe even 100 nanometers in diameter. And while this is also happening, you can have the formation of nanophase iron particles as well. Again, these as the solar wind is implanting, it's breaking bonds that the iron has with other structural elements in these regolith phases, and those iron atoms may then be free to diffuse together and form these metallic iron nanoparticles. And so here's just kind of an overview of what a solar wind damaged rim may look like. We have vesicles, we have some nanophase iron particles. One thing I didn't mention is that we have the presence of solar energetic particle tracks that can be retained in the crystalline grain interior. Those are occurring due to our higher energy solar energetic particles that are emitted during high energy events like solar flares. And so it's within this defect-rich space-weathered rim that we would expect our implanted solar wind species to be retained. Here's an example of that disordered rim that we might see. The atoms are not perfectly aligned. We have some other defects in here like vesicles. And so we can have trapping of those implanted species, either physically, such as interstitially in vacancies and whatnot, or in the case of hydrogen, which can bond, bonded to oxygen. And so this is how it's been thought and predicted that we would have retention of these species in our space-weathered regolith. This would happen on the moon as well as any other airless body that's exposed to the space environment. And so now going from the grain scale, I'll expand a bit out to our larger scale effects of solar wind irradiation. Again, we have it's causing sputtering, redeposition of that sputtering, amorphization of material, vesiculation, and the implantation of these solar wind volatiles. So one of the effects that we can see at the global scale is through spectroscopy and remote sensing is this darkening and reddening of the regolith, which is primarily what is thought of as the effects of space weathering. You can see this basaltic material has these diagnostic absorption bands, but compared to soil collected from the same site, the soil is redder, darker, and has weaker bands overall. And that's due to the formation, largely due to the formation of the nanophase iron particles. As I mentioned before, we also observe the introduction of this hydration phase, this 3-micron band, which could be observed, which is indicative of either OH or H2O. And we also have this introduction of exogenous volatiles to the moon. This could be noble gases that have isotopic ratios indicative of the solar wind. This could be hydrogen as well as some other species. And from there, once they're introduced into the regolith, they can be cycled in a variety of ways, either get gardened and be retained deeper into the regolith, or once they're in the regolith, they could be released and enter the exosphere. Or they could even, in the case of water and some other volatile species, ballistically hop across the surface and make its way into other sinks, such as cold traps or polar ices. And so with that, what are some of the outstanding questions that we have regarding the storage of these volatiles in regolith grains? For one thing, we still have not had a really good understanding of what their physical trapping environment is within those space-weathered rims, or in some cases how they form, primarily in the case of OH and H2O. And also, is there a relationship between volatile content and other parameters such as composition, mineralogy, maturity, surface temperature? There are varying relationships with these parameters depending on the remote sensing data sets or corrections applied to those data or modeling parameters that may be applied. And so can we address some of these discrepancies with analyses of the samples? And also, we want to understand how well are these volatiles being retained in the surface, such as during daytime heating, micrometeorite impacts, and other processes that will affect the regolith as well. And so the way that we can address this is with analytical techniques that can identify these volatile species and spatially resolve where they are being stored in these regolith grains. And so recent advancements such as transmission electron microscopy, atom probe tomography, and nano secondary ion mass spectrometry have started to address some of these questions. And today I'll be talking about some of our work using TEM and atom probe to address these questions. So moving on to the first section of this work is talking about that water, the storage of that solar wind derived water in the lunar regolith. And so just to give you a bit of a primer on what we can do with transmission electron microscopy is we can study structural and chemical effects of space weathering. Here's an example of transmission electron microscope that we use at Purdue. For scale, I am about this tall, so this is more than double my height, but I'm also not that tall either. That's why I've grown out my hair to give me a couple inches. But with the TEM, we can perform a lot of analyses, such as imaging of microstructure. Here's an example of an agglutinic grain in the TEM. This dark line indicates the surface. These white circles at the top are vesicles, and then we have other veins and other phases present in the interior of that grain as well. We can do chemical analyses such as elemental identification and see the enrichment in some of these veins they're containing iron, titanium, oxygen. We can also do high resolution imaging to look at the defects and crystalline structure of our materials. And we can also get other crystallographic information using electron diffraction to further understand what these materials are made of at a structural scale. And one of the main techniques enabled in the transmission electron microscope that I'll be discussing, and it's because of how we've used it to identify these solar wind volatiles, is EELS, electron energy loss spectroscopy. And so the way that this works is like with all the TEM techniques, you have an accelerated electron beam that is transmitted through your sample that we prepare with a focused ion beam to be less than 100 nanometers thick. And in the case of EELS, that transmitted electron beam loses some amount of energy, which is diagnostic of its interactions with the electrons present in the sample. And so eels can give us different types of information, such as electronic structure, bonding environment, oxidation state, and chemistry. And so in this case, I'm talking about identification of some light elements that is difficult for us to identify using other traditional techniques used in Earth and planetary sciences. And EELS has previously been used to identify solar wind volatiles in space weathered material. First being on the left, the identification of hydrogen and water in the space weathered rims of interplanetary dust particles, as well as the identification of solar wind helium in vesicles in space weathered lunar oxides. And I'd also like to give you a little bit of a primer on atom probe tomography. So atom probe tomography enables us to get near atomic chemical information of sample volumes that is complementary to TEM. As you can see from this nice rotating movie, we can get three-dimensional information. We can also quantify ions at near atomic resolution, and we can reconstruct chemical trends in the sample volume, such as depth profiles of species. And in some cases, we can also resolve structural components like nanophase iron particles or vesicles, seen here. An atom probe has also been used to start to study space weathered materials. It's identified the presence of hydrogen, water, and OH in an immature space weathered lunar olivine. And it's also been used to identify hydrogen, OH, and H2O in a space weathered olivine grain from asteroid Itokawa. So moving on to some of our work, the sample that we're looking at is Apollo soil 79221. This is a mature Mare regolith sample, has an I sub S over FeO of 81. And this is a scoop sample collected from the sunlit surface. And one thing I'd like to note, because of its implications for the retention of these species, discussed later on, is that this surface reaches daytime temperatures of up to 385 Kelvin on at this sampling site. So moving on to some of our results. Here is TEM and EELS analyses of a space weathered olivine from this grain. Here's an example of that space weathered rim with our carbon protective layer. This dark material is a platinum protected sputter coated layer, and we have our solar wind damaged rim here with vesicles and defects present in it. And here are a couple images of some vesicles in this rim that we used, that we analyzed using EELS spectrum imaging. And here are some representative spectra that we've pulled from this region showing the presence of water by this feature around 8.6 electron volts. So this is what an EELS spectrum looks like. It's on the x-axis is energy loss, and on the y-axis is intensity. And so this energy gap of water feature is diagnostic of the presence of water. This hydrogen K-edge is diagnostic of the presence of hydrogen. And we can also see helium. This helium K-edge is diagnostic of the presence of helium. And so we see the presence of water in these vesicles, these darker areas here. And particularly in the blue, orange, and red spectra in these vesicles. And we could see a weak hydrogen feature present in a couple of these vesicles pulled out here. And we could see not as present, but maybe still there, weak water feature present in the rim material as well. And aside from just pulling spectra from individual pixels, we can also map the distribution of these features as well. And so this was performed using principal component analyses, and we could see the presence of this water feature mapped strongly into these vesicles that I've outlined in this white circle and outlined again in those TEM images as well. The presence of that hydrogen feature also maps closely with the presence of those vesicles, as well as this helium feature as well. So we could see storage of these hydrogen, water, and also helium in these vesicles in the space weathered olivine. and it's in higher abundances relative to the rest of that space-weathered rim. Moving on to some of the atom probe results. Here's an example of a two-dimensional slice of a reconstruction of the olivine sample that we analyzed. At the top, this purple and yellow is our platinum protective coating, and we sampled around 130 nanometers deep into the grain, so capturing our space-weathered rim. And we've identified the presence of hydrogen, OH, and H2O. Here are some depth profiles and depth concentration profiles extracted from this cylindrical region of interest here. And overall, we can see a somewhat decreasing trend in the concentration of these species with depth away from the grain surface. And we can also see, in some cases, peaks, spikes of concentration superimposed on this overall trend of decreasing concentration. And so what we've done with this is gone in and used small 5 nanometer diameter regions of interest, as you could see in this movie here, to try to pull out the concentration of these hydrogen species in those regions. And so throughout the depth of this profile, we identify the presence of different regions of atomic density that we classified as voids, being low atomic density, clumps or clusters being higher atomic density, random being our more characteristic atomic density, as well as we extrapolated some values from the base of the grain as well. And so we could see a distribution of the concentration of these species with atomic density here. And we could see those lower atomic density ROIs corresponding with our voids having a somewhat greater concentration relative to our characteristic and denser regions as well. And we could see that those base values have lower concentrations of these values, consistent with that depth profile that we saw before, showing the decreasing concentration of these species. And so both EELS and Atom Probe are showing us that we are retaining hydrogen and water in these space-weathered rims, and are also showing us a greater concentration of these species in these vesicles in the rims. And so what does that mean? Does that make sense? Does that correspond with some other, or what influence does that have? And does it connect to some of the other observations made through remote sensing and modeling efforts? In the case of hydrogen, this matches up nicely with some recent studies using molecular dynamics to start to understand the diffusivity of implanted solar wind hydrogen in samples, and starting to incorporate more microstructurally accurate parameters, such as the presence of defects and voids in these materials. And so here's an example from Morrissey et al. Of how they're doing that. Here's a void present in in this case, amorphous silica, and they put hydrogen atoms on its surface and see what happens if there's diffusion when it's held at 1000 Kelvin. And they could see that there's still retention of these hydrogen atoms at the surface of these voids during this heating event, showing that these types of defects are more retentive of hydrogen than just bulk material that is not taking into account the microstructural complexity of these materials. And so moving on to water specifically, and why we might be having higher concentration of these species in the vesicles, I'd like to first mention this process of recombinative desorption. So recombinative desorption is one of the primary mechanisms hypothesized to form solar wind-derived water on the surface. At a larger scale, it's proposed that you have your implanted hydrogen going into regolith grains where you have oxygen bonded with some metal cation. That hydrogen will then diffuse to the surface via random jumps between oxygen that has dangling bonds, and eventually get an accumulation of these hydroxyl groups at the surface of the grain, where these neighboring hydroxyl groups may combine and react and form H2O, which would then get immediately lost from the surface. Yeah, and here's just those steps broken down. And so that desorbed water may then be lost to the exosphere, may reabsorb onto grain surfaces, or maybe escape to other sinks on the lunar surface. So this is a surface. This process requires some type of surface for these hydroxyls to accumulate and react. And what do we know? We have all of these surfaces inside of our grain interiors in our space-weathered rims. And so we're proposing that this recombinative desorption mechanism may also be occurring within the space-weathered rim at the surfaces of these vesicles, so that you have hydrogen diffusing through the rim via random jumps. It may attach to the surface of these vesicles, react, the neighboring hydroxyls may react and form that molecular water that would then be trapped inside these vesicles. This process is also proposed to drive the formation of molecular hydrogen as well. And so this could also be a way that we're getting molecular hydrogen in these vesicles as well. And once you have the water in there, then you can have that water be adsorbed potentially on the interior surface of these vesicles. You could also have the accumulation of hydrogen and OH at these vesicle surfaces as well. And so extrapolating out to larger scales, what effects might this have? And so these more complex defects would have higher potential to trap the implanted hydrogen and water. And this is known as activation energy of these sites. And so the effects of different activation energies, which may correspond to how strong those defects bind the hydrogen and water, can have very strong effects on the retention of hydrogen and water across the lunar surface. And here are a few examples of that model distribution across the lunar surface using different activation energy ranges. This lower activation energy results in a low concentration of surface hydrogen across the lunar surface, particularly at low and mid latitudes, and can also create a strong diurnal variation. But when models incorporate higher activation energies, potentially representative of our complex defects, we could see that the overall concentration of hydrogen is much greater. At all latitudes, we can see the presence at low and mid latitudes, and it ends up reducing the strength of that diurnal variation as well. Another result that we have from the atom probe tomography measurements, in this case on an agglutinic grain, is we can also see the retention of these species in the agglutinate, but one thing that's particularly interesting is that this nanotip captured a titanium iron-rich vein, and in this vein we could see a depletion of these species in that region, which may mean that we have not as strong retention of these species in our more titanium-rich phases. And this also supports some remote sensing observations of the lunar surface, especially from Voller et al. You can see that they've observed that there is overall lower concentration of water in the titanium-rich maria. And also there's a stronger diurnal dependence on the water content in the titanium-rich maria as well. It's also been noted that that process of recombinative desorption is more efficient at lunar surface temperatures relevant for titanium oxide relative to silicon oxide. And so it could be that we have greater loss from our titanium-rich phases of water relative to our silica-rich phases, like our olivine, agglutinates, plagioclase, other silicate materials. And we've also seen this retention of the water in our space-weathered grains, and this could be contributing to the observed molecular water component observed in grains by SOFIA observations of the lunar surface as well. Those have observed a retained water component during day and night cycles, and they propose that it could be retained in impact glasses, but we're showing that this could also be the retained water component could also be contributed by the water observed in these space weathered rims. So the main takeaways of this work is that with coordinated nanoscale analyses, we've identified the retention of solar wind derived H, OH, and H2O, and we observe higher concentrations of these species in vesicles. Vesicles and other defects may drive the production of water and retention of that water inside of space weathered rims. And some variability in the nanoscale trapping environment may also be influencing the behavior of hydrogen and water at the global scale. And this work is currently in review at EPSL, and hopefully it'll be out soon for you all to read that. Shifting gears a little bit, we're moving on from water to neon, and I'll talk a little bit about some other noble gases as well. So in the case of neon, we've previously identified this in the lunar regolith and in the lunar exosphere based on isotopic analyses. We could see this is primarily concentrated in our soils and subsurface samples that have isotopic analyses closest to solar wind and fractionated solar wind. And as I mentioned before, there's also been observations of solar wind neon present in the lunar exosphere. It's been observed that solar wind neon is particularly concentrated in fine-grained regolith. Of all the lunar materials analyzed, the highest solar wind neon concentrations are seen in regolith samples. And these are particularly concentrated at our finer grain size fractions. And so based on this connection with regolith, particularly finer grained regolith, which has greater surface to volume ratios, it's expected that this neon is being trapped in solar wind damaged rims, which has also been supported by noble gas analyses as well. So again, we're using eels to identify the presence of this neon in these space weathered rims. In this case, we have a different feature in the same energy region that we were looking at before. This is the neon L23 edge, present at around 16.8 EV. And so we've identified the presence of this neon in vesicles within an agglutinic grain in this Apollo sample. So here's an example. Here's a TEM image of that agglutinic grain. Up here is the grain surface, and we could see these dark areas are vesicles present close to the surface. And here's a zoomed in image of that region there at the surface. And we performed, in this case, line scans across vesicles and observed the presence of that neon feature within these vesicles, but not present outside of the vesicles. And this supports previous studies that have shown that agglutinates are identified as a particularly neon-rich phase in the lunar regolith. We've also identified this neon in, again, this regolith, but in this agglutinate, but in a different phase instead of that amorphous glass phase. This is in a titanium-rich, iron titanium-rich vein present in the grain that is intersecting with the surface. And so within this vein, we could see within the upper surface the presence of vesicles, nanophase iron particles, as well as vesicular nanophase iron particles. And in a few of these vesicles, we could see the presence of this neon feature at around 16.8 EV that seems to be absent in the vein material. I'd also like to note that we don't really see the presence of a water feature or hydrogen feature in this phase, which could also be, again, indicative that there is less retention of those species in these more titanium-rich phases. So we can see a variation in the retention of different solar wind volatiles based on composition of the phase. And like helium, it's been observed, neon concentration also correlates with titanium oxide concentration. And again, we can also map the distribution of this feature in some of these regions in the rim. And we could see that the presence of this peak matches closely with the presence of vesicles in some of these areas. The shape and intensity of this and the energy position of this feature can also vary based on uh, the pressure or the abundance of the gas in these vesicles as well. And so relating this to some other work, it's been observed in some noble gas analyses that there is a high temperature release of neon from some space weathered lunar regolith grains. There is primarily low temperature release, probably due to neon being sited interstitially in different defects, but this higher energy, higher temperature peak could be indicative of higher activation energy sites where this neon is being stored, like the vesicles that we're seeing and the neon trapped within it. So that has interesting implications regarding these types of noble gas analyses and the diffusivities of these different species that we may be deriving from these types of analyses at the bulk scale. So this could show that there's an important connection that may need to be made between these larger scale bulk analyses of extracted gas and connecting these to our nanoscale observations to see where this neon or any of these gases may be sited and be stored inside these grains. And I mentioned this before, but there's also, we observe retention of these of solar wind neon, solar wind helium, as well as our other noble gases in the regolith, also in core samples. And these core samples show an almost independent depth profile of these species, meaning that in this case, this core sample in the regolith that it was extracted from was well mixed over these times, over the time scales that would have mixed it, and that we see pretty consistent concentration, meaning that there is retention of these species over the time scales that you'd have this gardening occurring. So kind of to summarize this neon work, the neon as well as helium are and the other noble gases are non-reactive gases, so they can tell us about the physical trapping conditions of these space weathering signatures, and we could then extrapolate that to this idea of activation energy and trying to improve our models of the retention of these species on the lunar surface. Again, we're seeing retention of these species in grains that experience near maximum daytime surface temperatures, which could indicate that there's a long lifetime of these grains exposed at depth, exposed at the surface, and that they may be retained in grains gardened to depth, and that you may need higher temperature processes like micrometeorite impacts to release these volatiles from these higher activation energy sites like these vesicles to be released into, for example, the lunar exosphere. And so that is a good transition to the last part of this talk that I'll mention, is trying to understand the retention of these solar wind volatiles in lunar regolith grains during micrometeorite impact events. So just briefly, again, I've mainly focused on solar wind irradiation, but our other primary space weathering process is micrometeorite impacts, which are hypervelocity dust particles impacting the lunar surface. And so this can produce melting and vaporization of material and the deposition of that material onto grain surfaces like you see here. Can also form nanophase iron particles and vesicles during this process as well. You could also have the breakdown of regolith material and the formation of agglutinates, which are these welded fragments of precursor mineral grains and melted material, and also progressive gardening of the regolith as well. And so are there connections between this process and our volatiles that have been observed? Yes. One strong example of the direct observed relationship between meteorite impacts and solar wind volatiles is the release of water into the lunar exosphere observed during these micrometeorite impact events. This was observed by the LADI mission that saw a correlation in the timing of meteoroid streams hitting the lunar surface and water released into the lunar exosphere. And modeling results have also shown that the long-term lifetime of the retention of these species on the lunar surface is limited by the likelihood of micrometeorite impacts hitting any particular area of the lunar surface, which has been modeled to be around 4,000 years based on micrometeorite fluxes. So we've seen that there's release of water into the exosphere during meteorite impact events. We've also studied impact products for their volatile components. It's been observed that lunar agglutinates have a solar wind-derived hydroxyl component present within them based on SIMS analyses as well as by reflectance spectroscopy. So it's been thought that this hydration could be retained during that impact event. However, some other analyses that have happened more recently on Chunga 5 impact glasses have shown that based on the isotopic signature of hydrogen species present and their distribution through the interior of these impact glasses, show that there's not much retention of that precursor water present in these impact glasses, and that the hydrogen species observed are implanted subsequently after that glass bead formation by solar wind implantation. So do we have retention of these species in impact products? Not maybe, but maybe not as well. And as I mentioned before, we've observed trapping of these solar wind volatile species in our nanoscale features, vesicles being one of the primary storage sites identified in these space weathered grains. These vesicles were initially predicted to form due to the coalescence of implanted volatiles during heating events. And I'd also like to mention that I didn't talk about before, the presence of another solar wind volatile carrier phase, if you will. These vesicular nanophase iron particles have been also observed to store helium as well. And so what would be happening to these features during micrometeorite impacts? Well, for one thing, experiments have directly shown the formation of vesicles during rapid heating events that simulate the thermal effects and timing of micrometeorite impacts, such as the formation of vesicles in lunar grains, shown here. Experiments have also shown, these are transmission electron microscopy images of lunar grains, and it's also shown the formation as well as destruction of vesicles in the space-weathered rim upper surface of a lunar regolith grain during slow heating events as well. So micrometeorite impacts, these heating events have been shown to be essential for the formation of our main solar wind volatile carrying phase. But similar experiments have also been shown to destroy these features as well. This are similar rapid heating events performed on a Murchison particle, which is a CM2 chondrite, which was irradiated with hydrogen and then subjected to rapid heating events inside of the transmission electron microscope. And after one rapid heating event, you could see the onset and formation of vesicles in these lighter regions here. But after a second rapid heating event, these vesicles are destroyed. And so likely any volatiles present within them would be lost from the grain. So kind of the question that we're trying to address is, are these solar wind volatiles being retained in lunar grains during this impact event? Macroscale and modeling predictions suggest that they may not be. Sample analyses of impact products don't necessarily definitively say one way or the other. And one of our main carriers of these volatile species, the vesicles, can be shown to be formed during micrometeorite impact events, but also be destroyed during micrometeorite impact events. So any volatiles that are contained within them may follow those trends as well. And so the way that we are testing this question is by using this in situ heating within inside of the transmission electron microscope on space weathered lunar grains. We're doing these experiments at the University of Arizona using the Hitachi TEM there, which has a specialized holder to hold TEM samples prepared for TEM analyses, this specialized holder is used for heating, and we are subjecting these grains to rapid heating events from room temperature to 1,000 degrees Celsius in 1 second and back down to room temperature in a second. And so here's an image of what those chips look like on the holder. And all the way in the middle right here is an example of one of our cross sections of a lunar grain prepared and transferred onto one of these heating chips so that we could observe the changes to the volatile content and distribution present in the space weathered rims of these grains. And so this is still ongoing work. We just performed our first analyses this past summer. And so I'll share with you a bit of our preliminary results, but keep in mind that this is still ongoing work. And so one of the effects that we see, this is a STEM image collected beforehand, an annular dark field image showing the presence of vesicular iron nanoparticles at the grain surface, as well as other nanophase iron particles present. And after being subjected to heating, we could see the agglomeration of pre-existing iron nanoparticles into larger nanoparticles and the formation of new iron nanoparticles. This is consistent with previous experiments that have done similar types of heating events. But what's interesting particularly is the agglomeration of these vesicular iron nanoparticles shows that the vesicles present in the nanoparticles are lost. And so those vesicles are being annealed, likely meaning that any of the helium present inside of those vesicular iron nanoparticles is also being lost as well. And so we could see one of the main carriers of the solar wind helium identified in these lunar regolith grains are being altered, and that this helium is likely being lost during these micrometeorite impact events. And another preliminary result that we have is the possible retention of this helium still in these space weathered grains after this heating event. Here are examples of some eel spectra, again, with a weak feature around 22 EV, which is representative of that helium K edge. And so while we are seeing loss of helium from one of these main space weathering signatures that's known to store it, we may also be seeing retention as well. So there could be conflicting processes happening during these events, which would correspond with some of the previous expectations from larger scale analyses and modeling. And so we're still performing these analyses, and we'll be doing so on different phases, such as olivine, pyroxene, ilmenite, our main lunar phases, to see what's happening with these volatiles, particularly focusing on the volatiles that we've analyzed, such as identified previously, such as hydrogen, water, helium, and neon. And so with that, I'll leave you with some larger takeaways from this work. So we've shown that we can directly identify the nanoscale storage of solar wind volatiles in space weathered lunar regolith grains, and that these nanoscale analyses can be used to ground truth and inform some of the remote sensing observations and modeling studies on the behavior of these volatiles at the lunar surface. Additionally, some of the relationships that we see in volatile content and things like grain microstructure and chemistry could also be influencing some of the global variability seen in the behavior and retention and cycling of these volatiles. And that space weathering processes likely contribute to the volatile cycling within the regolith and to other sinks at the lunar surface, such as the poles as well as into the lunar exosphere. And that space weathering is not just important for darkening and reddening, as has largely been the motivating reason to study it, but we're showing that it can also control the surface volatile behavior on the moon as well as other airless bodies. And so I'd just like to acknowledge NASA JSC curation for the sample and the facilities used in this work at Purdue, Ohio State, Northwestern University, Johnson Space Center, and the University of Arizona. I'd particularly like to highlight that the facilities at NASA Johnson Space Center and the University of Arizona were enabled by the Planetary Science Enabling Facility Program, and this work was supported by NASA Solar System Workings and the Finest programs. Thank you very much, and I'd be happy to take questions.
Thank you so much, Alex. That was fantastic. So yeah, we'll open it up for discussion and questions. Autumn, go ahead.
Oh, I was just clapping. I thought it was a great talk. Great job, Alex.
Thank you.
Any questions? Here.
Alex, this is, if you can hear me, this is John Bradley. Really beautiful,
Hi, John.
very beautiful work. And I have an observation, and please don't take it as a criticism, but signal to noise is clearly a challenge in the detection of some of these species using eels.
Mm-hmm.
And in the case of neon, have you confirmed the low loss detection with the high K edge at, I think it's 850 EV for neon?
Not yet. That's some analysis that we're planning to do soon. Our eel system is unfortunately down at the moment, but that is something that we're looking to do to confirm this measurement in these samples. And we're also planning to do some irradiation of some standards with neon to compare those edges as well.
And I noticed that it appears that water gives a feature at 8.6 EV, but not a hydrogen feature, the K edge. And hydrogen, conversely, gives just the K edge at 13 EV. So are you saying that the water and hydrogen features are mutually exclusive of one another?
Yes, from what I've seen and from my understanding, I don't think that you necessarily need a hydrogen K edge to confirm the presence of water. That hydrogen K edge arises from the electron from the hydrogen, and if it is bonded to another atom that's not hydrogen and gives up that electron, you may not see that hydrogen K edge. So when we observe it with the water feature, it may be due to there being other hydrogen present in the vesicle, or perhaps dissociation of the water that we see inside of the vesicles with eels.
Okay, thank you. Once again, very beautiful work.
Thank you, John.
Brittany?
Hey, Alex, how are you doing? Great talk. I had a question about the third project with the MEMS chip. So, what temperature did you take that up to again?
We brought it up to 1,000 Celsius.
Okay, that's what I thought. So we used to bake our lunar samples prior to putting it into the neon when I was at NRL, and I found that even those low temperature, like 120 degrees Celsius, would detrap the helium from the vesicles. So I'm wondering if you used maybe like a lower temperature, you might see like an intermediate stage where you're getting coalescence of the nanophase iron and maybe preserve some of those vesicles even.
Yeah, so some of the previous work done with this, like by my advisor Michelle Thompson and her work in 2017, showed like with slower heating experiments and ramping up that temperature, you could see formation of vesicles and of the nanophase iron at some intermediate temperatures. We've had ideas to do some of these intermediate temperatures, but we wanted to start with kind of this higher extreme to see whether there would be retention or loss of these volatiles to compare to some of the larger scale implications. If we see full loss, then maybe we would try to use a lower temperature to see if we might see a transition with that. But for now, we want to use that higher temperature extreme to as a first estimate.
Okay, great. Thank you. Good luck.
Yeah, thank you.
And then Roy? Roy, you might be muted. Maybe Roy, you could put your question in the chat. Chip, do you have a question?
Alexander, this is a great talk. Thank you again for presenting it at our seminar. I'm sure all the survey people appreciate your work, and non-survey people too. The one quick question I had was, what is the eventual, what happens to the volatiles associated with the micrometeorite impactor? Is that lost or transported to the poles or incorporated in the regolith?
That's a good question. And I think that one that's still trying to be addressed. I think there have been some isotopic studies in the case of hydrogen species that Stefant and Robert 2014 study I mentioned that has seen negligible contributions of chondritic water to the lunar surface, and that most of the hydrogen species that they were detecting were solar wind derived. There have been, interestingly, there was a talk at MetSoc this year looking at the oxygen isotopes of water in of lunar samples and seeing that the oxygen may be sourced from meteoritic components. And so there may be some retention of the impactor volatiles in the regolith, but it's unlikely, and that may be lost into the lunar exosphere or ballistically transported and be deposited at the poles. And that's why missions like Viper, which should hopefully continue, that may be able to isotopically distinguish the sources of the origins of the volatiles there, may be able to address those questions.
Zach, you got a question?
I have a quick question. You showed a picture which was depth on the y-axis and the concentration of xenon, krypton, helium, neon on the X. And for the heavy rare gases, they're actually lower concentrations at the surface, which I'm guessing is because they're not being supplied by the solar wind. Is that right? And the others are increased. Yeah, there you go, at the surface. So if that is the explanation that they're lower, I mean, the xenon and krypton are lower because they're being lost, then you would think that with some kind of gardening, this would kind of propagate down. Maybe it does, maybe it's just noise there. But, you know, you'd think that if you're losing the krypton, xenon, and then that gets gardened back into deeper levels, it would be lower there as well. And maybe it is. I didn't realize that it's so noisy now.
So the overall concentration or abundance differences among the noble gases is largely due to their overall abundance in the solar wind, with helium being the most abundant and decreasing with our heavier noble gases. And so those overall concentrations are likely, differences across the noble gases are likely due to that.
Yeah, okay. And so you have the increase at the surface, but then as it gets gardened back down, it's lost again by micrometeorite impact or something.
Yeah, in some cases you could see some loss, but I think generally that's somewhat consistent. With depth, there's some variations in that. But I think the study was generally saying that I read and got this from was saying that this the abundance of these noble gases is relatively independent of depth, and from that they're extrapolating it to mean that this regolith is well gardened
Okay.
Well, I think that does it then for questions. So again, thank you so much, Alex. So a round of applause.
Thank you very much.